Welcome to the Deep Dive, your shortcut to being well-informed. Today we're diving deep into how large language models, LLMs, might finally break free from using just text to talk to each other.
Yeah, we're talking about these multi-LLM systems, setups where you might have one model that's great at coding, another for math.
Or just general knowledge, right?
Yeah.
But the way they usually interact, well, it's been a real bottleneck.
That's the traditional text-to-text approach, T2T. Basically, inside, these models have this incredibly rich, high-dimensional understanding.
Okay.
But to share anything, they have to squash all that complexity down into a flat sequence of text tokens. Then the other model has to try and reconstruct the meaning.
It sounds, lossy. Like saving a detailed vector graphic is a blurry bitmap every single time.
That's a good analogy.
So the big question the researchers tackled is fundamental. Can these powerful models communicate more directly, beyond just text?
And the answer seems to be yes. They're proposing a new way called cache-to-cache, or C2C. It's about direct semantic communication using something called the KV cache that's already part of the LLM, holding those rich internal states.
Interesting. Okay, let's first really unpack the problems with the old way, T2T. You mentioned the bottleneck.
Right, the information bottleneck. That compression-decompression cycle inherently loses semantic detail. Complex ideas get flattened out.
Especially when different specialized models are trying to collaborate, I imagine.
Exactly. Nuances get lost in translation, literally.
And it's not just data loss. There's also ambiguity, right? Natural language is just inherently fuzzy sometimes.
Very much so. Think about pronouns, idioms, context, things humans handle easily but can trip up rigid protocols between AI agents trying to work together.
The source material had a good example, the coder-writer scenario.
Ah, yes. So the coder model needs the writer model to use a specific HTML tag, like P, for a paragraph break.
Okay.
In T2T, it sends that instruction as text. But the writer might misunderstand P. Maybe it thinks it just means start a new section generally, not the specific structural meaning the coder intended.
Because the text alone didn't carry that precise, deep context. So the output gets messed up.
Precisely. With C2C, the idea is the coder doesn't need to fumble with words to explain P. It can transfer that specific semantic understanding directly into the writer's KV cache.
Much more direct. And this friction, this back-and-forth text generation, also causes latency, doesn't it? It's slow.
Oh, it's fundamentally slow. Every single message means one model has to generate text token by token, sequentially. Then the other model reads it. It's like sending messages by slow mail.
Okay, so T2T is lossy, ambiguous, and slow. Definitely seems like we need something better. How did they prove the KV cache was the way to go? The Oracle experiments.
Right. They needed to validate the core idea first. Could the cache even hold this enhanced semantic meaning effectively? The first experiment looked at the benefit of cache enrichment.
How did that work?
They wanted to see if they could boost the semantic quality of a cache without making it physically larger in memory. So they compared two setups, a direct one where the model just saw the question X, and an Oracle one where it first saw some relevant examples, E plus the question X.
Right.
But then, crucially, they removed the cache parts related to the examples E, leaving only the cache for the question X. So the final cache size was identical to the direct setup.
Ah, I see. So same size cache, but one was sort of primed with more context initially.
Exactly. And the result, the Oracle setup showed significantly better accuracy, like jumping from about 58% to over 62% on one task with the exact same final cache length.
So the cache itself became richer semantically even after the extra context was gone.
Correct. It confirmed the cache can be a high-quality semantic embedding.
But it wasn't uniform, was it? The effect varied across the model's layers.
That was a key finding. This enrichment effect wasn't the same everywhere in the transformer architecture. Trying to enrich all layers wasn't optimal. Yeah, selectively enriching just the top-performing, say, 10 layers gave better results than enriching everything. And if they tried enriching the worst-performing layers, accuracy actually dropped.
So it's not just about dumping information, it's about targeted injection.
Precisely. Surgical precision matters.
And the last piece of the foundation, convertibility. Could one model's cache thoughts be translated for a totally different model?
Yes. They needed to show this wasn't just for identical models. They trained a small neural network, just a 3-layer MLP, to map the KV cache from one model type, say, Qwen34B, to another, like Qwen30.6B, at different sizes, maybe different families.
And it worked.
It did. Visualizations showed the translated cache aligning neatly within the target model's internal representation space. So yes, you can convert these semantic states between different models.
Okay, so the groundwork is solid, the cache can be enriched, the effect varies by layer, and it can be translated. So how did they actually build this translator, this cache fuser?
Right, the cache fuser is the engine of C2C. It's the neural network tasked with taking the sharer model's cache, projecting it into the receiver model's space, and then merging it carefully.
Merging carefully, meaning not just overwriting what the receiver already knows.
Exactly. It needs to integrate the new information smoothly.
And the architecture has three main parts. First, projection.
Yeah, that's fairly straightforward. It takes the sharer's cache and the receiver's current cache, does some processing, basically preparing them for the merge.
Then the dynamic weighting module. Sounds like it controls the volume.
That's a good way to put it. It uses a clever technique, an input-aware head modulation layer, to dynamically adjust how much influence the sharer's cache has based on the specific input. It's adaptive.
Okay, makes sense. And the third part, the learnable gate, like an on-off switch per layer.
Sort of. It's a trainable value for each layer that learns whether injecting the sharer's context at that specific depth is beneficial for the task.
So it learns the optimal injection points.
Right. And during training, it's a smooth value, but for actual use, at inference time, it effectively becomes a binary choice. To inject at this layer or don't. Very efficient.
Makes sense. But building this also meant solving some practical alignment problems, didn't it? Like models using different dictionaries, different tokenizers, token alignment.
Yeah, that's a hurdle. If models split words differently, you need a common ground. The approach was to decode the relevant text part to a plain string
Okay.
and then re-encode it using the receiver model's tokenizer. If one source token became multiple target tokens, they used a heuristic to pick the best match, maximizing coverage.
Got it. And what about layer alignment? If one model has, say, 32 layers and the other only 12?
They used what's called terminal alignment. The idea is to prioritize aligning the deepest layers first,
Why the deepest?
because those layers usually capture the higher level, more abstract semantic understanding. So you align the final layer of the sharer with the final layer of the receiver, then the second to last, and so on, working backwards.
Aligning the most abstract concepts first. Okay, so a lot of careful engineering went into this. Did it pay off? What were the performance results?
They were pretty significant. Quantitatively, C2C systems showed average accuracy gains of about 8.5% to 10.5% compared to the models working individually.
Wow, that's substantial. And compared to the old T2T communication.
Still a solid win. C2C outperformed T2T by roughly 3.0% to 5.0% in average accuracy across the board.
And crucially, the speed.
Yeah.
The latency issue.
Big improvement there. C2C was, on average, about 2.0x faster than T2T. Getting rid of that sequential text generation really speeds things up.
That 2x speedup is huge in practice.
Absolutely. And there was a really interesting case mentioned where they used a sharer model that wasn't well fine-tuned for instructions.
Oh, what happened?
In the T2T setup, this model would sometimes just ignore the task and generate tons of irrelevant long text. Just noise. But with C2C, because the communication bypassed that messy text generation step, the system worked fine. It successfully used the underlying knowledge without suffering from the sharer's poor instruction-following behavior.
That shows real robustness, handling even difficult or slightly broken model partners. What about mixing different types of models?
That's where C2C really shone too. For instance, pairing a general model like Qwen3 as the receiver with a specialized coding model, Qwen 2.5 coder as the sharer.
A heterogeneous pairing.
Right. C2C gave an average 8.59% accuracy boost over T2T in that kind of setup. The complementary knowledge transfer is clearly valuable.
And there was that physics problem example, Coulomb's law. That seems quite telling.
Yes, that was a great illustration. Both individual models failed the problem. The T2T setup, even when given a text hint about the inverse square law, it still couldn't calculate the right numerical answer.
But C2C.
The C2C model, receiving that core understanding of the inverse square relationship directly via the cache transfer, actually implied the logic correctly and got the right answer. It wasn't just getting a hint, it was getting the understanding.
That really highlights the difference between text suggestion and semantic transfer.
Yeah.
So digging a bit deeper, why does C2C work so well? The ablation studies tried to isolate this, right?
They did. And the key takeaway was that the main benefit comes from the complementary contextual understanding provided by the sharer model, especially when it's a different specialized model.
So it's not just about having more parameters to train in the fuser network?
No, they tested that. Even using the same model as both sharer and receiver, self-communication via cache, gave only a small boost. The big jump came from integrating genuinely different external knowledge.
So we're truly enriching the receiver's knowledge, not just helping it access its own information better. How did they measure that internal change?
They used a metric called effective rank. Think of it as measuring the richness or dimensionality of the semantic space represented in the cache.
Okay, like how many distinct concepts are encoded?
Sort of, yeah. And they found that after CDC fusion, the effective rank of the receiver model's cache measurably increased. For instance, the V-cache rank went from 532 up to 560 in one experiment.
That's concrete evidence then. C2C is literally expanding the semantic space of the receiver by injecting knowledge from the sharer.
Exactly. It confirms the mechanism isn't just superficial.
Okay, so wrapping this up, C2C really seems to demonstrate that LLMs don't have to be stuck communicating through the slow, lossy medium of sequential text.
Right. Using the KV cache offers a high bandwidth, low latency channel for direct semantic collaboration. It opens up possibilities for faster, smarter multi-LLM systems.
It feels like a pretty significant step forward for how these systems can work together.
It does. And maybe a final thought for you, the listener, based on that finding about layer selectivity. The research showed that often the best results came not from dumping all the sharer's cache, but by selectively augmenting only a subset of the receiver's layers, sometimes sparsely.
Only injecting knowledge where it's most needed.
Precisely. So the question to ponder is, how does this selective, optimized semantic transfer in AI perhaps mirror effective human collaboration? We don't just info dump everything we know onto a colleague. We usually try to share the specific insight or piece of knowledge that's most relevant to the problem at hand. Is C2C starting to figure out the AI equivalent of that targeted, efficient knowledge sharing?